Hello, my name is Alexis Martinez and I want to present my assignment 7. Sorry, there's a puppy in the background, so if you hear that. This assignment, I'm presenting my implementation of a graph to a model, a real-world system. The graph contains 20 vertices and 40 edges, and I utilize 3 different representations for the graph. Let's just go to the function header. My first implementation is an adjacent list, then I also did an adjacent matrix, and I also did an edge list. There are 3 different classes because I'll show you guys what ended up happening. And the graph models a transportation network between popular locations in Palos Verdes. So here is the image that I originally used. It contains parks, golf courses, and landmarks. Each edge represents a road connecting two locations, and the edge weights correspond to the distance between those locations. And the graph is supposed to allow us to analyze the shortest routes found and explore the connectivity. So here I ended up using Jupyter Notebooks really quickly to map everything out for us to clearly see and for me to check. And then I went ahead, tried doing it in Excel. That didn't work out, but I listed everything here for everybody to see. This is the names, the nodes. The weight is the distance between everything. And then if we go ahead and go to the testing, I have it here as well. These are the results that we'll explore in a minute. But for the visuals, I have everything here. I even have the edges we used, and I also have the code that I used to map the edges in the nodes compared to the real world one. And then I want to go ahead and jump into the different graph representations. So starting with the adjacent list. Yes, so these are the graph from the graph class. The adjacent list efficiently stores vertices and their connected edges. Each vertex is represented as a list of edges containing the destination and weight. This is implemented in the graph class where addEdge adds edges between vertices. That's here. In the adjacent matrix representation, the graph is stored as a matrix where the rows and columns represent vertices and the values at each cell represent edge weights. For unconnected vertices, I also used a high value of infinity to represent no direct path. And then if we go down to the edge list class, graph edge list right here, it stores all edges as a list of tuples in the format from, to, and weight. So next I'm going to explain the 3 algorithms in the edge list form. So starting with the Dijkstra algorithm, it's supposed to find the shortest path from a source vertex to all other vertices in the graph. Here's how it's supposed to work. So we have the distance vector. It's initialized to keep track of the shortest distance of each vertex. And then we have the priority queue in a min heap that stores pairs of distances and vertices. Then the while loop continues until all vertices have been processed. And if the current distance is greater than the already recorded distance, we skip this iteration because it's an outdated distance, and then the relaxation step checks all adjacent vertices of the current vertex. If the path through provides a shorter distance, then we update the distance list to the new value. So then going down to Prim's algorithm constructs a minimum spanning tree which connects all vertices to the minimum total edge weight. It works by growing the MST min span tree one edge at a time, always picking the smallest edge that connects a vertex in the MST to one outside of it. So with this, we initialize it with 3 vectors. The first being the key vector stores the minimum weight edge that connects each vertex to the MST. Initially, all key values are set to infinity, except for the starting vertex, which is set to 0. The parent vector keeps track of parent vertex for each vertex in the MST. This helps record the MST at the end. Then we have the in MST vector, which keeps track of whether a vertex has already been included in the MST. We start from vertex 0, setting its key to 0 since it will be the first vertex added to the MST. And then at each iteration, the algorithm finds the vertex that has the smallest key value and has not yet been added to the MST. That is Once all vertices are added to the MST, the parent vector is used to print the edges of the MST. Each edge is defined by its parent vertex and the current vertex. Then we have depth first search, is a traversal algorithm that explores a graph by visiting a vertex and recursively exploring all its neighbors. It helps identify connectivity and explore paths. I implemented DFS starting from the vertex 0 and used a helper function DFS util for recursion. The visited array ensures that each vector is visited only once, preventing infinite recursion, passes the starting vertex and the visited array of DFS util to begin the recursion. And DFS util recursively explores the graph from the vertex and prints each visited vertex. So the current vertex is marked as visited and its value is printed to track the traversal. The function iterates through all edges or neighbors of the current vertex stored in the adjacent list. If a neighboring vertex edge is not visited, the function calls itself recursively to explore the vertex. So then I just want to go over how we added the edges for the other representation. So for the graph matrix, we initialize a 2D matrix. All entries are set to infinity, representing that no edges exist initially. The diagonal matrix are set to 0 for the distance from a vertex to itself. And then the add edges adds an edge between two vertices from and to with specified weight. Since the graph is undirected, the matrix system, the matrix is symmetric. So then going to the edge list implementation, the edge list is everything represented as a tuple storing the edge. So the edge list is a vector of tuples that holds all edges of the graph, and the pushback adds the new edges to the list. So I'm going to go ahead and show you guys the main function. So we call each edge to go through each one, because I thought since we had different add edges functions for each class, I just used the same vertices and used their different class callings. And then I went ahead and timed each one once we called the functions. And yeah, I'm going to go ahead and run that now. So here is what it looks like. And then we have the timing for each one when it had completed the task. And now to go to the actual testing. So for the timing data, we ended up finding that the depth first search is just the best one to use overall, and the most efficient is the matrix depth first search, but also it wasn't just the fastest, it's just the best representation for dense graphs and clear visual analysis, because you can end up printing the rest of the matrices and seeing how things play out. The least efficient is Prim's algorithm with the edge list implementation. Even though it has a swap here, I took the average of 3 runs and I printed out the average times of the graphs in microseconds. So the data makes sense when you consider the time complexity, and then I have all of my sources here. Anyways, thank you so much for watching, and I hope you guys have a great winter break.